On this video, we're going to talk about integration by tables. So what happens is we've learned all these different techniques for solving integrals, for figuring out what antiderivatives are of different expressions. And as long as you're doing this all the time, that's pretty doable. But what happens is a lot of times people don't do this on a daily basis, but then they will have to find a particular integral. And so tables have been created to kind of serve as a kind of a recipe list for how to do different integrals for people that don't do it all the time and don't remember, integration by parts or trig substitution or U substitution and all the different things that we have learned here. So we're going to try to figure out how to use these tables, which are not as easy as it may seem like at first glance. So you will have these tables of values printed out. I'll give you a copy, or you can print it off the computer on your own. You'll have to use those as you do these homework assignments, and you will be able to use these for certain parts of the test. So let's see if we can first take a look at that integration tables, that Appendix C, the integration tables, and you can see they've been organized by different classifications of integrals. So as you page through there, you should see the U to the N section, followed by an A plus BU section, and each of these here that follow. So I think there's 1, 2, 3, 4, 5, 6, 7 different sections. So you have to, when you're faced with an integral, first decide which section does it seem like it's most likely to fall under, and then you have to look through there and try to figure out of those choices which one best fits your integral. And then I'm going to ask you to identify that by telling me, what number formula are you using, and then I can try to follow along with your work and see if you have done that in the appropriate way. So as I do these, we're going to work some examples here. You may want to pause it as we go through it, and you try to find the formula first, because it's a little harder to do on your own than it is if you're just listening to somebody else do it and you're like, oh yeah, I can see why that is the correct choice. But making that decision on your own takes a little bit of practice. So here's our first example. The integral of dx over x times the square root of x minus 1. So if you look in that, you will find this, I believe, in the section where it's labeled a plus bu. So if you look in that section, then number 17 is the formula that we want. And so I would expect you on a homework or test question to write that down, that number 17. And so the formula says, and you don't have to write the formula down, but the formula says 2 over the square root of negative a, and then arc tangent of the square root of a plus bu all over negative a plus c. So there's our formula, and so what I would expect you to do is to communicate what is the a, what is the b, what is the u, and what is the du. So in this particular case, the a is going to be negative 1, and the b is going to be positive 1. Our u, it's a function now, is just x, and that makes du equal to dx. So when we then plug all of those into our formula here about what the integral is going to be, we should get 2 arctangent of the square root of x minus 1, and then plus c, our constant of integration. So that's the process that I would expect you to go through and how you would show your work for me. So I want to, in particular, know which formula you decided to use, how you decided what you're going to call each of the different parts that appear in the formula, and then, of course, your final answer also. Okay, let's try sliding up and doing another example. So here we have the integral of x times the square root of x to the fourth minus 9 dx. So as you look through there, you should hopefully find the match that we want here is going to be number 26. And that says that the integral of the square root of u squared minus a squared du is going to be 1/2, and then we have brackets. It'll be u square root of u squared minus a squared natural log of the absolute value of u square root of, u plus the square root of u squared minus a squared, and then plus c. So in our scheme here, our u is going to be x squared because we want the u squared to give us that x to the fourth. That means our du is going to be a 2x dx, and we're going to get that the a in our case is going to be 3 because we want a squared to be that 9. So that means our integral is going to become, so our integral of x square root of x to the fourth minus 9 dx is going to be converted into, we've got the x for a moment. We're going to make that u squared minus a squared with our choice of u and a, and then our du over 2x, we'll replace our dx by du over 2x. That will account for our extra x there, and we'll pull that 1/2 out. So we're going to get to 1/2 the integral of the square root of u squared minus a squared du. So now we have maneuvered it so that it's going to match our formula, and so our answer is going to be this extra 1/2. We'll multiply that 1/2, so our answer is going to have a 1/4, and then we're going to get x squared times the square root of x to the fourth minus 9, and then minus 9 times the natural log of the absolute value of x squared minus the square root of x to the fourth minus 9, and then our plus c. So there's a little bit to this. It's not quite as simple and straightforward as it might seem at first. Let's try another one. So here our integral is x over 1 plus e to the negative x squared, and then we have a dx. So if you take a look for this, you might want to pause it because it'll take a little while. We are going to look in the e to the u section, and hopefully you will find that number 84 is going to match this. And that says the integral of du over 1 plus e to the u will equal u minus the natural log of 1 plus e to the u plus c. So in our scheme then, the u is going to be that exponent, negative x squared, and that's going to make du equal to negative 2x dx. So our integral, which is x over 1 plus e to the negative x squared dx, is going to become, well, we'll leave that x for a moment, and we'll call that 1 plus e to the u. The dx is going to get replaced by du over negative 2x. So that's going to allow us to account for that extra x that we saw. And so we can pull the negative 1/2 out, so that'll be a negative 1/2, and then our integral becomes the du over 1 plus e to the u. That's the match for our formula. And so we will get then negative 1/2, that extra constant, and our u is going to be the negative x squared. We'll get a minus the natural log of 1 plus e to the negative x squared, and that will end the part that's going to get distributed over, and then plus c. And so that's going to be our, or if we want, I guess, we can either leave it like that, so that's one possible version. You can also distribute that negative through and make it look a little more aesthetically appealing, and call that 1/2, and just call it x squared plus the natural log of 1 plus e to the negative x squared plus c. So either of those will work. I think that's all I've got on this panel. Okay, let's go to the next one. I have an extra panel, so that 4 is going to be blank. I goofed that up. So let's look at the second panel. So here we are going to talk about rational functions of sine and cosine. No, that's not what I want yet. I think I've got more up here. We're going to get to that first. Reduction formulas. So reduction formulas, several formulas that we'll find on this table have the form that the integral of f of x will be g of x plus a second integral. So these are called reduction formulas because they reduce the original integral to the sum of a function and then what's hopefully going to be an easier integral. So everything we do here is going to be using the tables. So let's see what we have here. So we have the integral of x to the third sine x. So if you look there, I think you can see that number 54 will be a match for this one. And 54 says the integral of u to the n sine of u du will be equal to, and then it's going to say a negative u to the n cosine of u du plus n times the integral of u to the n minus 1 cosine of u du. So you may recognize this as coming from integration by parts. So we have in our scheme here, u is going to be the x. That makes du equal to the dx, and our n is going to be 3. So the first time we do this, we are going to get negative x to the third cosine of x plus 3 is our n times the integral of, and now we have x squared cosine x dx. Now we're going to have to, I'm going to change colors just so you see. Now we're going to look for this on a table, and this one is going to now be number 55. So they're in that same group. That says the integral of u to the n cosine of u du is equal to, u to the n sine of u minus n times the integral of u to the n minus 1 sine of u du. So I'm going to slide the panel up a little bit here. So in this one, then we have that our u is again going to be x, and the du will again be dx, but this time our n is 2. And so we're going to get that original, we still have that original negative x cubed cosine x, and now we're going to go plus, and that's going to be 3 times our x squared sine x minus 2 times the integral of x sine x dx. And so then we'll go to I'll change my color again here. So this now integral here we can see is hopefully number 52. And that says the integral of u sine of u du is going to be sine of u minus u cosine of u plus c. So our u is going to be x and our du is going to be dx. So we have still that original negative x cubed cosine of x, and now when we distribute there, we'll get a plus 3 x squared sine x, and we're going to get a minus 6, and then that's going to be times that sine of x plus, or is that a minus? I think it's a minus, then x cosine x plus c. So finally a negative x cubed cosine of x plus 3x squared sine x minus 6 sine x, and that'll become a plus 6x cosine x plus c. I'm not sure that would have been any quicker than us doing integration by parts on our own, but that's how we're going to use those tables. And then I'd like you to, at every step, tell me, how you're going to, which formula you're going to actually use, as well as what you're going to call the various parts of that integral. Okay? Let's see what else we got here. So now we have the integral of the square root of 3 minus 5x all over 2x dx. So if you look for that, I think that the match for that is going to be number 19. And that says the integral of the square root of a plus bu all over u du is going to be 2 square root of a plus bu plus a times the integral of 1 over u square root of a plus bu du. So in this case, we are going to choose, I'm going to go right here. The a is going to be 3. Our b is going to be negative 5, and our u is going to be x. So that means, and we're just going to pull that 2 here outside. So we're going to say that the 1/2 integral of the square root of 3 minus 5x all over x dx, that's going to be the way we're going to refer to our original integral, is going to be, we're going to need that 1/2 times all of this stuff. And so that's going to be then the 2 square root of 3 minus 5x plus 3 times the integral of, and our new integral will be 1 over x times the square root of 3 plus 5x dx. Whoops. And so now, and let me end that bracket there. So now we have to find an integral, a formula that matches this integral. And I think that's going to be number 17. And so we're going to get that we have, what do we have here? So our formula is saying that the integral of 1 over u square root of a plus bu du is going to be, and for us, let's see, our u is going to be x, our a is going to be 3, and our b is going to be 5. So we get a choice. We have these two branches, and the a greater than 0 branch, which is what we have, is that upper one. So that's going to become 1 over the square root of a times the natural log of the absolute value of the square root of a plus bu minus square root of a all over square root of a plus bu plus the square root of a. So we're going to have, let's see, we're going to distribute this 1/2 times these things so we can separate this out. So that's going to get us to just the square root of 3 minus 5x. That was our first part. Then we're going to get 3/2. That's the 1/2 times 3. And then we're going to get our 1 over square root of a is going to be 1 over the square root of 3. We're going to have that times the natural log of the absolute value of the square root of, and that's going to be, oh wait, I should have said back here that the b is -5. That would have made that more clear before. So the b is actually a -5 there. Okay, so then we're going to get the natural log of our a plus bu is going to be 3 minus 5x in the radical, minus the a is going to, or the square root of a is going to be the square root of 3 for us, all over, and our a plus bu is again going to be the square root of 3 minus 5x, and this time plus the square root of b, which is u. So that's where we're going to get, and that's our final answer right there. Okay, so now sometimes when we try to match these integrals that have sines and cosines in them, it's hard to find a match, so we're going to have a couple of strategies here. One is, and this is where our that formula that we have that I put on the top of that 7.3 worksheet there. So there's a double angle formula that comes up occasionally for us, and so I don't expect you to have it memorized, although it is pretty memorable, but we're going to need it here, and we'll need it from time to time. So we'll trade that in now to call that 2 sine x cosine x in place of that sine of 2x, and then we have 2 plus cosine x in the denominator. But when you look for that, there's nothing really that quite matches it with all the trig formula sections. And so in this case, sometimes what we want to do is make a u substitution first and not try to do this integral as if it were trig functions, but as if it was a rational function. So since we have that cosine x in the denominator, if we say u is cosine x, then du will be a negative sine x dx, and so our dx will be a du over negative sine x. So then if we make that substitution first, then we're going to get the sine x we're going to leave for a minute, but the 2 cosine x is going to be 2u. I'm going to leave that sine x for a moment. This becomes 2 plus u, and then our du will account for that extra sine x there. So that is going to then make this integral. If we pull that negative outside, or we can even pull the negative 2 outside, then that's going to become just whoops, there's my left hand bumping that where I don't want it to. So that's going to become negative 2 times u du over 2 plus u, which if we look around, we can see that is going to be in the form, which one is that? We're going to see that's actually going to be number 3. And so when we do that, we're going to get the negative 2. And then according to the formula, that's going to be our u, which is cosine x, minus 2 natural log of, there's our 2 plus cosine x, and plus c. And that's going to be our answer. Or if you want to distribute, we could call it, I guess, negative 2 cosine x plus 4 natural log of 2 plus cosine x plus c. Might be a little bit nicer. Okay, I think that's all I have on this panel. I got one more that's going to be kind of tricky. Okay, so if you can't find an integral that matches the form, let me back up. Is that where I'm starting? Yeah. So this is going to be a substitution where we have, if we have these sines and cosines, and we can't find anything that matches it, and even if you try the use substitution like we did in the previous example, and you still can't get anything to match, there's a special substitution that we can use just for sines and cosines. So what that says, let me bring up my pen here. So what that says is if we make a special substitution that u is equal to the tangent of x over 2, which we're really going to skip over that, and this is really, there's a half angle formula if you, and I don't know how you would remember it. I wouldn't remember it back from your AP prep days. But there's a half angle formula for the tangent of x over 2 that says it's equal to sine of x over 1 plus cosine of x. So if we start with that substitution, then we can get to cosine x is equal to 1 minus u squared over 1 plus u squared. Sine x is 2u over 1 plus u squared, and the dx becomes 2 du over 1 plus u squared. So you can try this special substitution, and that will hopefully turn that integral that had sines and cosines that just didn't match anything into something that doesn't have any sines or cosines at all, and will just match some other formula that we can then actually do that integral, and then once we get the integral, come back to it. So what I'm going to do here is just prove why these substitutions work. That is why when we choose u to be tangent of x over 2, which is equivalent to saying u is sine x over 1 plus cosine x, that these substitutions follow. When you actually use this, you don't have to do any of this proof. You will just come right to this part here and just plug those in and then try to solve the resulting integral. So I'm going to show you the proof for that first, and then we'll come back and do an example of how we might actually use that. So first we're going to try to show that when we say u is equal to, so when we say u is equal to sine x over 1 plus cosine x, how it follows that cosine x is going to become 1 minus u squared over 1 plus u squared. So starting with where we are, we're going to square both sides of the equal sign. So that's going to become u squared on the left, and that's going to become sine squared x, and we'll get a 1 plus cosine x quantity squared. Then we're going to trade in that sine squared for 1 minus cosine squared x. That comes from our favorite trig identity. Sine squared plus cosine squared equals 1. Then we can factor that numerator as the difference of two squares and call that 1 minus cosine x times 1 plus cosine x over that 1 plus cosine x quantity squared. That will allow us to cancel one of those 1 plus cosine x's, and so what we have is that u is right now equal to 1 minus cosine x over 1 plus cosine x. So we're making progress. Remember, we're still trying to get that cosine of x is equal to 1 minus u squared over 1 plus u squared. So I'm going to multiply both sides by 1 plus cosine x. So that's going to become u times 1 plus cosine x is now equal to 1 minus cosine x. And then we can distribute that u, and so that's going to be u plus u cosine x is equal to 1 minus cosine x. Now we have two terms with cosine x and two terms that don't have cosine x. So I'm going to add the cosine x to this side and subtract the u to that side. So that's going to be u cosine x plus cosine x is equal to 1 minus u. Is that what I want? I think that's what I want. Oh, I goofed up back here when I squared both sides. That was a u squared and I dropped that off. Sorry about that. Let me fix it. So that's a u squared. So that's a u squared. Okay, so now that's a u squared and that's a u squared. I was going to have a hard time getting to what I wanted there. Now, on the left side, we can factor out that cosine x, and that will leave us with a u squared plus 1, and that's still equal to 1 minus u squared. And so then we'll get to divide to get the cosine x by itself. And so that's going to become the 1 minus u squared on top, and I'll write that as a 1 plus u squared on the bottom. So that's where that comes from, and this is what we're going to use right here. When we see a cosine x, we're going to replace it by a 1 minus u squared over 1 plus u squared. Okay, let's figure out how to get the second part. We can get that sine x must be 2u over 1 plus u squared. So we're going to go back to, let me try to save it. So we're going to go back to our u equals, I'll do a different color here. So let's say that u is equal to our sine x over 1 plus cosine x. So we will say that our cosine x we know is now, no, we'll just multiply the 1 plus cosine x to the other side. So we get u times 1 plus cosine x is equal to sine x. And now we're going to replace our cosine x by what we said it was equal to here. So that's going to be u times, and that's going to become a 1 plus, and then we have a 1 minus u squared over 1 plus u squared is equal to our sine x. So then we can get a common denominator inside that parentheses. I'm going to slide that up a little bit. So we have u times, and that's going to be a 1 plus u squared over 1 plus u squared plus our 1 minus u squared over 1 plus u squared is equal to sine x. So when we add those numerators, the u squareds are going to cancel each other out. And so we are going to get u times, and we've got a 1 over 1 plus u squared is our sine x. And I think that's what we wanted, wasn't it? Where did our 2 come from? Oh, because we had 2 of them, because 1 plus 1 is 2. There we go. And so that's how we get that sine x is going to be 2u over 1 plus u squared. So that's that second substitution that we have. And the last one is we're going to try to show, so since we're running out of room here, I'm going to kind of rewrite it here. So we're going to try to show that our dx is going to be 2 du over 1 plus u squared. So here we are going to go and say that we said we're going to use our tangent of x over 2 substitution. So if we then solve for x, then we're going to say that the arctangent of u is x over 2, and that means that x is going to be 2 times the arctangent of u. So that means now if we differentiate with respect to x, we'll get dx on the left is going to be 2 times, and if you remember, the derivative of arctangent of u is going to be du over 1 plus u squared, and so that's our 2 du over 1 plus u squared. I'm going to rewrite it as equal to dx that we were after. Okay, so let's see how this actually works. So let's do an example here. We're going to say we want the integral from 0 to pi over 2 of 1 over 1 plus sine of theta plus cosine of theta d theta. Okay, so if you look for those on your tables, if you look in the trig part, there's just nothing that's quite like that. And this doesn't lend itself well to a u substitution like we did earlier, where if you say u is sine of theta, then du, there's just no good place to put it in there. It's just not going to work well. So that's why we're going to try to do the new substitution that we're given. And this is on your integration tables at the very end. So we are going to say then that sine of theta is going to be the 2u over 1 plus u squared. Our cosine theta we are going to replace by 1 minus u squared over 1 plus u squared. And the d theta, that's like our dx, we're going to replace by 2 du over 1 plus u squared. Okay, so we have our integral is going to be, let's see, the d theta, well, let's go 1 over, this is going to be a mess to start with, so we have 1 plus 2u over 1 plus u squared plus 1 minus u squared all over 1 plus u squared. And here's our d theta is 2 du over 1 plus u squared. And do we dare change our limits to u limits as well? Remember what we said is that u is the tangent of x over 2. So we're going to make these be u of 0 and u of pi over 2. Okay, let's do some serious cleanup here. I'm going to slide this up a little bit. So our integral, let's see, if we put in 0 into our u, we get the u of 0 is going to be the tangent of 0, which is just 0. So that limit stays 0. U of pi over 2 is going to be the tangent of pi over 2 divided by 2 is pi over 4. That's particularly nice because that's going to be 1. Now, as we imagine distributing this 1 plus u squared into the denominator here, and the 2 is going to multiply there, this is going to become 2 du in the numerator, and we'll get a 1 plus u squared plus 2u plus 1 minus u squared in the denominator. You with me there? So this is going to become integral 0 to 1 of 2 du over, and it looks like the u squareds are going to cancel, and we'll get the 1 plus 1 is 2 plus 2u. Oh boy, this is nice. So we have the integral from 0 to 1. If we factor a 2 out of that denominator, it will cancel with that 2 up there, and we have maneuvered this now to be 1 over 1 plus u du. And let's see, can we find, and I guess we can just integrate that. We do okay with that and just say that's going to be the natural log of the absolute value of 1 plus u that we're going to evaluate from 0 to 1. And so that's going to be the natural log of 2 minus the natural log of 1. And we know the natural log of 1 is 0. So after all that, we get that. Kind of cool.